Welcome back, everyone. So today, I think we'll mostly be talking about searches of gravitational waves. So Priyanka will start with science with CBC. What kind of science can you do with these particular kind of systems, which is this compact binary systems? And then Costa will talk about match filtering, which is basically used to search these gravitational waves. Because as we discussed yesterday, these systems have a lot of noise, and the signals are buried in a noise. You need a lot of tools to actually dig these signals out. So today we'll mostly focus on that. If you have any question, please ask us right away, or you can write down your questions and we will make sure that we come back to those questions and discuss those thoroughly. Okay?
Hi everyone. So welcome to the next day of this session. So I'll be starting with science with CBC or compact binary coalescence. So if you have any quick question, just ask in between. And if you have any long question that needs more explanation, just write it down and ask me at the end of the talk. So let's begin. So here are some outline of my talk. So I'll first talk about what are compact binary coalescence, what we mean by compact binary, and the gravitational waves that we get from this compact binary coalescence. And in the second part, I'll be talking about the events from this compact binary coalescence that we detected from LVK, LIGO-Virgo-KAGRA collaboration so far. And the final part of this talk is what science we can do with this observation and what can you learn about our universe from this detected gravitational wave from compact binary coalescence. So this is the first part of my talk, what are CBC and gravitational wave from CBC. So in the background, you can see two black holes. So these black holes, I'll talk about in details what this compact means, but here you can see these black holes, they're very compact and they're in a binary, and when they merge, we call it compact binary coalescence. So there can be different sources of gravitational waves. In a broad sense, we can divide this gravitational wave in two categories. One is called this transient gravitational wave signal, which is a short duration gravitational wave signal, like short means seconds to minutes or maybe hours. And there can be long duration gravitational wave signal, which are like days, months long. So based on this CBC, that compact binary coalescence, that's come under this transient gravitational wave signal. And you can also divide this two different category in model source and unmodeled source. So model sources are basically the sources which we modeled already and we have good idea of how the waveform looks like and we can detect easily. And the unmodeled source that we don't know how to make the model and we are still trying to do that. So this compact binary coalescence that comes under the short duration and it is very well modeled. That's why we detect them mostly in the LIGO-Virgo collaboration. And there is this continuous gravitational wave or long duration gravitational wave, which are also well modeled, that comes from this continuous emission of spinning neutron star that we also call pulsars. And in the unmodeled category, we have burst-like sources. One of these images from the supernova explosion, which are transient like short signal, but they're unmodeled. And we also have unmodeled sources, which are long in duration, which is the stochastic gravitational wave background, which is essentially the gravitational wave from the unresolved sources, like the let's say you have many weak signal, they overlap and then they becomes this stochastic, they create the stochastic gravitational wave background. So in our talk, we'll be focusing on gravitational wave from this particular category. So before going to compact binary coalescence, let's see how this compact object actually form in our universe. So you start with this stellar nebula. Nebula is essentially a cloud of dust and hydrogen gas and ions and all. So from this stellar nebula, you get stars, main sequence stars, and these stars are their lifetime is depend on this hydrogen burning, which we call fusion. And then when the hydrogen is it's over, it becomes red giant, and then it turns into the planetary nebula, and finally you get some object called white dwarf. So to get this particular evolution, you have to start with low to medium star mass. Let's say if this main sequence star has mass less than 8 solar mass, Then this star goes through all this process and become white dwarf. And this final product, white dwarf, has mass range of 0.6 to 1.4 solar mass and density in this range. And this white dwarf is supported by electron degeneracy pressure. Now, if your main sequence star is very high mass star, let's say if your main sequence star is more than 8 solar mass, then it goes under this same hydrogen fusion and then becomes red supergiant, and then it evolves to supernova. And if your progenitor star is high mass star, like 8 to 20 solar mass, then it becomes neutron star. And if your progenitor star is very high mass star, like more than 20 solar mass, then it becomes black hole. So depending on the star you start with, the end product, it can be neutron star or black hole. So in our detection, we mostly care about this neutron star or black hole because they are very, very compact compared to this white dwarf. So some properties about black holes and neutron star. So black holes, as many of you know, these are regions in space-time with very strong gravitational fields, and so strong that even light cannot escape from this particular thing. And this is a black hole image that is captured by this Event Horizon Telescope. This is black hole in the center of M87 galaxy. So depending on the masses, you can divide the black hole in different category. So the first one is the stellar mass black hole, which has mass around 5 to 100 solar mass. So the stellar mass black hole, they are created by the stellar evolution of the star. There is also intermediate mass black hole, which have mass, let's say 10 square to 10 to the 5 solar mass, which the stellar evolution cannot create. And to create this intermediate mass black hole, you need to have many merger of this compact object to form this very high intermediate mass black hole. And there is supermassive black hole, so which has mass around 10^6 to 10^10. And for this particular black hole, this is a current research topic, that how these supermassive black holes are created, because these are so heavy that neither this solar mass and not this merging of black hole can produce this high. So there are different theory on that it can happen that this black hole accretion between the mass and it can produce this high mass. But most of the galaxies have supermassive black hole in their center. And there are one more category called primordial black hole, which is essentially the black hole that formed right after the Big Bang. So come to the neutron star. So neutron star objects are also as dense as black holes, but they are mostly made of neutron. And the core is so dense that this proton and electron, they just squash together to become a neutron. And the density of this neutron star is so heavy that you cannot create this kind of dense matter anywhere in the earth. So we don't know still what is the equation of state of this neutron star, how this matter behave in this extreme condition. So these are also kind of current research topic that people are working on. Also, the neutron star can have like if the neutron star is spinning around its axis, then it can have it can rotate, and we call it pulsar, and it can also have the magnetic field, which we call magnetars. So here I showed some movie which shows this compact object. Here, these two black holes, they're rotating around each other in spiraling, and then finally they merge. And you can see the space-time around it, it's wrapping, and it becomes in equilibrium after the merges, after some time. And the gravitational wave that looks of the gravitational wave that comes out from this merging black hole, you can see the gravitational waves are coming to the coming outward and traveling to the infinity, and then finally it merges and becomes a stable black hole. So I guess from yesterday tutorials, you guys are familiar with this kind of waveform, how it looks. So there are different stages of this compact binary coalescence. The initial stage, when the two objects they are far from each other, they are in spiraling, that is called in spiral stage. In this stage, the gravitational wave look like this, and then they radiate the angular momentum and the orbit strings, and they come close to each other, and then finally they merges and settles to one single black hole. So the waveform looks something like this. You can see the amplitude that is increasing till the merger, and then it decays in the ring down. So to model this gravitational waveform, to understand these signals that we get from this compact binary coalescence, we need theoretical template to understand the signal. We need to know what we are searching for. So what we do, we assume general relativity to model this kind of system, to understand how this waveform looks. And in different part, we use different kind of approximation methods and different ways to solve these different phases. So for the in-spiral, we use something called the analytical approximation, post-Newtonian approximation. And to model this merger part, we use numerical relativity because the system during the merger, it becomes so dynamical that you cannot use any approximation method to model those particular phase. So you solve the full Einstein equation to model that particular merger part. And for the ring down, because it becomes a single black hole with some distortion, you use something called black hole perturbation theory to model this ring down phase. And from yesterday also, as we saw, gravitational wave amplitude, it scales with total mass and inversely proportional with the distance. So here I have a demo to show how it actually looks. So you guys can see, right? So this is the blue curve is a signal that data from you get for the gravitational wave, and this yellow is the template that you are trying to fit with your gravitational wave. So what you do, you try to vary your total mass and distance so that your template, the yellow curve, matches best with the blue curve. So here I'm going to do that. So with total mass, the gravitational wave, the duration increase or decrease. So I'm trying to fit the total mass so that it best matches my waveform. And then I need to fit the distance so that the amplitude also matches. So if I decrease the distance, so you need to do some fine tuning to get that. So here in this test, it's not exactly, but you can see near the merger part, the gravitational wave there matching quite well. So this is how you do scaling with total mass and distance to match your template waveform with your actual signal that you get. So let's go back. Okay, so this gravitational wave from CBC, because they are coming from this compact object, they also encode the information of the source parameter. So from seeing this gravitational wave, you can answer this question: what are the masses and spins of the compact object that merges to become a final object? What are the mass and spin of the final object that you get? And how far is the source from you? What is the luminosity distance? What is the redshift? Because universe is expanding from Big Bang theory, we know. So what is the redshift of the sources? And if the merger involved neutron star, then the neutron star form with matter. So if there is some matter in some gravitational field, external gravitational field, there will be some distortion in the shape, and that is called tidal deformability. And so if there is neutron star, then you can answer how compact is that neutron star if it is quasi. And also this compact object, they form in some kind of environment. So this environmental effect also imprint in the gravitational wave itself. We'll talk about more regarding all these things, but let's just move forward. So that ends the first part of my talk, with what is compact binary coalescence and the gravitational waves, how it looks from this compact binary coalescence. In the second part, I'll be talking about the gravitational wave from this compact binary that we detected by LIGO-Virgo-KAGRA so far. Okay, so the first detection of this gravitational wave happened in 2015, and after that now it becomes a routine to observe this gravitational wave from CBCs. So here is a diagram that shows the timeline of different observing run and what detector was running at that particular time. So you can see this O1, O2, these are the observing runs, and the years corresponding to this observing run, you can see. And in each observing run, what detector was active. So let's say for O1 run, LIGO Hanford and LIGO Livingston was active at that time. And you can see how it progressed. And the bottom plot, it shows the gravitational wave event that is detected in all these observing runs. So this different color grid shows the different observing run like O1, O2, O3. And till O4A, we have confident detection that we can tell, okay, those are coming from the compact binary. And this O4B and C, they are still kind of under process. So you can see the compact object we detected from O1 to O4A, it's around 218, sorry. And there are even from O4B and C. So total, we have around 400 events so far detected by LIGO-Virgo-KAGRA collaboration. So in the right plot, I'm showing a masses in the stellar graveyard. So here the y-axis shows the solar mass. I don't know if you can see it because the color is so contrast. So these are like solar mass from 1 to 200. And this x-axis doesn't mean anything. It's just to create some room to make this plot and put this masses and all. So this blue color shows the black hole that are detected by LIGO-Virgo-KAGRA collaboration. This red, these dots, you can see these are the black holes that are detected through electromagnetic observation. And this yellow dots, you can see dots, these are the neutron star that we detected through the EM observation, and the orange one are the neutron star detected through LIGO-Virgo-KAGRA collaboration. So you can see there are a lot of events that we detected. Also another thing to point here, this arrow you can see, so it actually means that this arrow is pointing to from one to another and then becomes so this is one black hole, this is another black hole, it merges and creates the final black hole. So this is the arrow represent. So you can see there are a lot of black hole events detected and very few binary neutron star events we detected. And also if you observe carefully, you see there are very little black hole or neutron star in this region, which is like around 2.5 to 5 solar mass. I don't know if you can see the scale. So it's very few black hole or neutron star in this region. So from the observation, there is something called mass gap in this particular region that we observed very few black hole or neutron star. And yeah, we'll talk about this later in details. So here is a plot of this gravitational wave detected within this 10-year period from 2015 to 2024, and this each block shows each event, and this is for different observing run O1, O2, O3, O4, and the third peak you see it's like the gravitational wave and frequency time representation. So this peak means there is a gravitational wave. The nature is like a chirp kind of nature that we discussed yesterday. So some of the events are very loud that you can clearly see the chirping nature, and some of the event are not that loud, so but they're still here, they're still present. You just cannot see because the SNR is, the signal to noise ratio is low for this event. So I also have a movie that shows the gravitational wave that are detected from the CBC for this 86 event in the GWTC4 catalog. And this is done by a success collaboration. So let's just play the movie. So what you see here is that 86 event with two new black holes, they're merging and producing some final black hole. And these things you are seeing, these are basically the gravitational wave that emits from these sources. So it's in spiraling and then finally merges, and yeah, that's it. Okay, so let's start with the first event that we detected, first binary black hole detection, which is GW150914. So this basically means 14th September 2015. So this event in gravitational wave, they're encoded like this: year, month, and date. So this particular event was detected in 14th September 2015. That's why the name. So obviously this was a very groundbreaking invention through the LIGO detector. So this first event that is detected, so this first binary black hole that is detected, that has initial black hole masses of 36 solar mass and 29 solar mass, and it merges and becomes a final black hole with 62 solar mass. So if you add these two black hole masses and if you subtract it with the final black hole masses, you see there is a difference between 3 solar mass, and this 3 solar mass was transferred in gravitational wave, gravitational emission. So this is the gravitational wave in the detector look like, and you can see a frequency time pattern here, a chirping signal. And this is a plot of showing the two black hole that is detected in this first detection, and you can see the gravitational wave it looks like. Also in the bottom plot, it shows that the velocities of these two objects as they in spiral and goes to merger, and the separation, relative separation between two objects. So as you expect, when it goes through in spiral and merger and ring down, the velocity will increase. So you can see this velocity curve is increasing. It can go up to 0.5 c speed of light, and the separation it decreases, and when it merges, the separation becomes almost zero. So, and these are the parameters, the black hole masses, secondary black hole masses corresponding to this particular event. Okay, the second milestone of LIGO-Virgo-KAGRA collaboration was the detection of binary black hole event. And it was also very special because this particular event has electromagnetic counterpart associated with this gravitational wave. So this particular event, GW170817, it was a merger of two black holes with mass range 1.17, and it merges and created 2.74 solar mass black hole. So this particular event was detected in 3 detectors: LIGO, Hanford, Livingston, and Virgo. And you can see a chirping like frequency signal. And for this particular event, the addition of Virgo was really important, because by adding one more instrument, you can localize the source better in the sky. So this gravitational wave detector, they are not sensitive equally in all direction. So when you have more detector, you can localize the source from where the particular source is coming in the sky better. And by doing so, if there is some electromagnetic counterpart associated with it, you can actually move your electromagnetic telescope in that particular direction of the sky to find out from where in the sky that particular signal is coming. So this was important for this event because this event has this electromagnetic counterpart, and this EM telescope, these are directional. This cannot observe a signal which is coming from an opposite direction if the telescope is in a completely opposite direction. So here are some parameters for this particular event. So this GW170817, it also called the multi-messenger event, so which is essentially observing a particular event in different messenger format. Like this event, it was detected in gravitational wave observatories also, as well as the electromagnetic telescope. So here is a plot showing the frequency time of this particular event. So this is the time to merger, and this particular black line shows the time where it merges. And just after 1.7 second of the merger, we observe this GRB burst, which is gamma ray burst. And this gamma ray burst was associated with this particular event. So this is important to study something called kilonova, which is a study of how this heavy element formed in our universe. So when the two neutron star merges, the neutrons which are inside this neutron star, it becomes free, and it goes through something called R process, rapid neutron capture. And in that process it produces a very high, very unstable and very high some kind of object, and then it start to radiate away, do some and it emits some optical transient which we call kilonova. And in that process, it creates this heavy element that we know in our periodic table, like platinum, gold, and others. Also, yeah, so this particular event was from this galaxy NGC 4993, and even after the merger, for many days we observed the spectrum of this particular event. We can see in different days how the spectrum look like. So if you go to if you observe this particular event in, let's say, 10 days, it becomes red, the spectrum, because it emits very high, you can see the formation of very high element in the process. So here is a just movie to show what happened during this event GW170817. So let's see. So you have two neutron stars which are orbiting around each other, and they finally merges, and you will see something. So the jet you are seeing, this is from this what is called R process and the kilonova that you get in your optical telescope. And this is where the formation of heavy element happen. So this is really a remarkable event to study. Okay, moving forward, so we observed the first binary black hole event in 2015, and then we observed the first binary neutron star event in 2017. Then we had to wait till 2020 to observe the mixed event. Mixed event means the event that is coming from neutron star and binary system. So this is the two events, GW20-0125 and GW20-0115. So these two events, these are from gravitational wave merger, gravitational wave from black hole and neutron star merger. And surprisingly, this two event was detected within 10 days of each other. So that was very nice. So you can see the sky localization of this particular two events, then the masses corresponding to these particular events. And then another one interesting event is GW190521. So this is the first event that shows that detects the that was the first direct observation of this intermediate mass black hole, which I was talking in the initial slides, that there are different kind of depending on the masses of the black hole, there can be different categories. So this intermediate mass black hole that we observed, which created from merging two black hole with 85 and 66 solar mass, and the final black hole mass was 150 solar mass. So we can actually show the existence of this intermediate mass black holes and through this observation. Also, another interesting thing about this event is that the two black holes that merged to form this heavy black hole, this 85 solar mass black hole. So there is, in the stellar evolution, it is not possible to create this heavy mass black hole. So there must be some other formation ways that these black holes are produced. So theory suggests that there can happen that this 80 solar mass black hole, 85 solar mass black hole, it may be created from merging of other black hole, not from the stellar evolution itself. So yeah, so this is very remarkable event to study this particular intermediate mass black hole case, and you can see how the signal look like in frequency time domain. Okay, so one more interesting event that I'm going to talk about is GW190814. So this particular event was from coalescence of 23 solar mass black hole and 2.6 solar mass compact object. Now, if you remember, in the initial slides, I showed that there is a mass gap between 2.5 to 5 solar mass. Like, we didn't observe enough black hole or neutron star in that region. So we don't know this 2.6 solar mass compact object, is it a black hole or neutron star? It can be either very high neutron star or too light black hole. So we don't know what is this object exactly. So yeah, that ends the second part of my talk, which is about the compact binary coalescence that we detected by LVK so far. So I'll pause here to see if you have some questions. Blind spot means? It can detect, but it is weak. Like, you cannot localize the sources better. So from every pair of detector, you can make a patch in the sky from where the signal is coming. So let's say if you have two detectors in two different sites, you can actually map a single patch in the sky from where it is coming. But if you have three detectors, then on top of that, you can get another patch. So the intersection between different patch will tell us the exact location of the sky. The gravitational wave detector is sensitive to all direction, but the localization area will be so large that you cannot say, like, you have to search for a longer time to see from where the signal is coming. But if you have more detector, the patch from where the the signal is coming, it will be shorter and shorter, so that it will be easy for the EM telescope to move. And otherwise, you have to search for in a long sky area patch, which is difficult.
I think question is slightly different. So are you thinking of it from the point of view of optical telescope, say? If you have optical telescope, you have to point it in one direction. Yeah, so that's what she said, that in gravitational wave, you don't need that. You don't need to point it in one direction. The gravitational wave can come from anywhere and you would still be able to detect it. But yeah, there is one argument that sensitivity can be different. Depending on the sky location of the source, your detector can be less or more sensitive. Okay, so because you have these antenna patterns. I will talk about it in my talk. So, but you can detect your gravitational wave, doesn't matter where it's coming from in the sky. Unlike optical telescopes where you have to be focused in a very small region in your sky.
Do you have any more questions? Right, I didn't go through that, yeah. So what happens is that if your the star in your stellar evolution is too high, so when it goes to, okay, let me go back to the initial slides. Yeah, here. So if your this mass star is, if the star mass of this star is too high, then when it becomes red supergiant, the energy in this red supergiant is so high that the sum of the photons energy converted to make the pair of electron and positron. So because of this change in energy, so what happens is that there is this radiation pressure that supports the star against the gravitational collapse. So when some of the energy of the photon transferred to produce the pair of electron and positron, so there is an energy gap, and this energy gap lead to some partial supernova explosion. In that process, what happens is that the star completely blown out without making any final remnant object. So there is no final remnant object in that process. The star just completely blown out in that system. So you don't see, there is no compact object in the end product. So, any more questions? Okay, I think we can move on. Okay, so having talked about what are CBCs and what we got in our detector, different event that we got. So what science we can do and what can we learn from this CBC detection in our detector? So when you detect some sources, the first question you ask, like, what are the source information? Like, what are the, so let's say you observe some signal here. The first questions will be, how heavy are these compact objects, from where this signal coming from? And are these objects are spinning? Like if they're spinning, how fast they're spinning? And where and when did they merge? So these are the basic questions that you will be asking from the observation in the first. So you want to know what are the source information. So for that, we do something called parameter estimation, which Neha will talk about tomorrow in details. So in the parameter estimation, what you do, you just calculate what will be the masses, mass ratios, and spins, like the parameter extrinsic and intrinsic parameter, and you try to do something called Bayesian statistics to get what will be your final mass, black hole, final objects, mass, and spins, and all other properties. So here are some results from this one of this paper, which shows these are the events, for like handful of event, and this the peak you see, the width you see, these are like the posterior distribution of what your mass can be, and this is not very sharp. So this is, there is some width, so that means there can be some uncertainty limit what the mass can be. And here is also some plot to show the primary and secondary masses of different events. So all these different colors are for the all event you see here, and there are some special event uh, for which the masses and spins are shown here, and this is one plot for chirp mass and spin. So this will be discussed tomorrow in details, how you do parameter estimation and so on. So the next thing we can learn from this detection is the binary formation channel. So as I said earlier, that the gravitational wave has some imprint of from where these binaries are formed and what are the formation channel, the environmental effect. So typically the binary formation channel can be divided into two ways. One is called isolated and another is dynamical. So in the isolated channel, you assume that you have two stars, and those two stars, they are already in the binary orbit, and they are revolve around each other, and in that process they become supernova. They go through supernova explosion, create the black hole, and then finally merges. Because this process is so long from the evolution of star to black hole and then merges, even if there is, let's say there was some initial eccentricity in the orbit, by the time they merges, the eccentricity radiates away in the gravitational wave form, and the final object you see may be non-eccentric signal. And in this process, mostly you see the spins of the binary object. If there is some spin, they're aligned with each other. You don't see some kind of precession or something like that. And there is this second channel, which is dynamical channel. So from the name, you can guess like this is a very dynamic process where there can be other stars around. So this process happens in a very dense globular cluster where there are other stars and other compact objects. So what happens is that the neighboring compact object, those can affect your binary evolution, and because of that, that can induce some eccentricity in the orbit. Also, that can induce some spin precession in the orbit. So this formation channel, it does imprint your gravitational wave. So here I am showing a waveform that looks like from a quasi-circular signal, like non-eccentric signal. So you can see the gravitational wave looks like smooth that you saw, and the amplitude is increasing and so on. But if your system goes to this dynamical channel, then there can be eccentricity, and then the signal looks something like this. So clearly you can see from the gravitational wave the changes. So you see some kind of peak and some bottom. So these correspond to the periastron apastron passage. So when you have eccentric orbits, sometimes they come close to each other, the energy release is high, and then when they're far from each other, the energy is low. So you can clearly, from the waveform, you can say what are the waveform and from which from which channel the compact object are formed. Sorry, the binaries are formed. Also, so if they're in isolated channel, you assume the waveform, the spins will be aligned with the orbital angular momentum. So the waveform looks something like this. But when you have dynamical channel, that can induce some precession, and you can see there will be some modulation in your amplitude in the gravitational wave. So this binary formation channel, you can learn about this, from which binary formation channel this binaries are formed from the gravitational wave detection. Okay. Next, we can study rates and population. So given you have many detection, now you want to see the populations of this binary object from your detection, from the observation. So we want to answer this question: how many black hole systems merge per cubic gigaparsec per year as a function of heaviest black hole mass? What are the distribution of black hole masses, spins, redshifts in this compact object? And what are the formation mechanisms in these LVK binaries? And do the mass gap really exist from the population? From the if you plot some population distribution, you can say if there is some mass gap that we predicted, and also you can answer the question how the universe, the rate of expansion of the universe. So how you do that? So you have masses, black hole masses from your observation. So what you try to do, you try to fit some power law using those masses. So you can use different power law. So here I'm showing like 4 power law, and you try to see which power law fits your data the best. So in our case, so this is one of the distribution. This shows the rate of the merger as a function of black hole mass. So you can see this particular power, distribution fit this kind of power law. This is power law plus peak, this kind of nature. And from this distribution, you can answer what's the smallest black hole that you can observe, and how does this 80 solar mass black holes form in the universe. Also, you can see as you go to high mass, this mass, the rate at which this black holes are merges, this also decreases. So you can see there is a mass gap clearly after this. So we talked about this mass gap earlier, that these heavy black holes that cannot be formed due to this paired instability supernova that we just talked about. So yeah, from the distribution, we can answer many questions. And also you can see there is some kind of substructure in the mass distribution. There is kind of peak. We don't know exactly why this, in this particular solar mass, this peak is happening, but there are many theories, many people are studying and answering. It may be due to the pair instability, it may be due to the low metallicity in the stellar evolution. So these are still open questions, and people are studying about this. So you can also do the spin, distribution of the spin from your detected gravitational wave, compact object, also the distribution of redshift. So all this population study you can do by observing many gravitational wave signal, and the more you observe, the more you can constrain your distribution to answer these questions better. One more interesting thing you can answer from your observation is that neutron star equation of stress. So as I mentioned, neutron star are very compact, very dense object. There is no way on Earth that you can produce this these dense objects. So these are very kind of laboratory objects to study how this matter behave in this extreme condition. So we want to answer those questions. Also, because the neutron star made of matter, there can be this tidal effect when it is in the gravitational field of other object. So then what is the deformability, tidal deformability, how much it will be deformed if it is in some other environmental field? So all these questions we can answer through the gravitational wave observation. So from the observation of GW17 or 817, we kind of constrain this how deformable or how compact our neutron star is. So from this observation, so this plot shows the tidal deformability of neutron star 1 and neutron star 2. So what it actually means is that the less the parameter of this lambda 1, the less your neutron star will be deformed if it is in some extreme gravitational wave field. So from this observation, we saw that the bright color here, it means that the neutron star in this particular system, they were like very compact, not very easily deformable. So this kind of questions you can answer by gravitational wave observation. Another interesting thing is this kilonova and heavy element formation that I already talked in some extent. So this kilonova is basically the merging. When the two neutron star merges, it goes through some process called R process, and in that process it creates heavy element, and you can see some optical glow, which is called kilonova. And in this process, it produces this heavy element. And if you see in this periodic table, so this different color shows the origin of this particular element in this periodic table. This hydrogen helium, they are created through the Big Bang fusion. And there are other origin of this element. But if you notice this color, violet, yeah, I guess. So this color shows the element which produced through the merging of neutron star. So you can see many of the heavy element in our periodic table, they come from the merger of the neutron star. So yeah, gravitational wave observation also helps us to study how much these heavy elements are formed through the neutron star merger. Also, we can study the cosmology with the gravitational wave. So we know the universe is expanding. That means the two objects, they are going far and far from each other. So if the universe is expanding, so you calculate something called Hubble constant, which actually tells us about the rate of the universe, rate of the expansion of the universe currently. So to calculate the Hubble constant, you need luminosity distance and the redshift. So luminosity distance is the distance of the event from you, and the redshift is, so because the universe is expanding, when the light is emitted by a source, when it comes to you, it stretches, it's redshifted when it comes to you. So if you have the information of the redshift and luminosity distance, you can calculate the Hubble constant. And this gravitational wave detection from compact binary coalescent sources, it gives you the distance, luminosity distance. So you know from where the mergers happen, the distance from you to the source, and also you can calculate the redshift indifferently. So as we talked about this GW17 or 817, which is electromagnetic counterpart. So if you know from where this counterpart is coming, from the galaxy, which you know, this NGC 4993, so you know the redshift of that particular galaxy. So from that, you can constrain the redshift and you can calculate the Hubble constant. But if you don't have the electromagnetic counterpart, still you can calculate the redshift by let's say you don't have any counterpart. So what you do, you have the distance of the source, and you know you have some sky area from where the source can be coming. So you can just map to some possible galaxies from where the source is coming, and then you use some probability theory to calculate what will be your Hubble constant, saying there is some galaxy in that particular direction. So this is one result that calculated the Hubble constant using the electromagnetic counterpart. So when you have electromagnetic counterpart, we call it bright siren because it is bright, you can see the EM counterpart. And when you don't have, the study called dark siren. So this particular result shows the constraint in Hubble constant. So this different colors shows the Hubble constant estimation using different method. And this solid line that goes through, this is the Hubble constant that is measured through this GW17 weight 17 event. So you can see there is a peak here. So from this GW17 and 17, we can constrain the Hubble constant around 70 plus minus some values. But you can see there is some difference between the Hubble constant that we measure from other method and from this particular method. So this is called Hubble tension, which is like you get different answer using different methods. So this is also shows different method you see, like bright side means you use the electromagnetic counterpart to calculate your Hubble constant. There is dark siren and dark siren plus bright siren. So in all this method, there is not very well overlap, and you can see there is some uncertainty in all these methods. So which is called Hubble tension. Okay, one more interesting thing and maybe very fundamental thing that we can do with the gravitational wave observation is test of general relativity. So initially I mentioned that our gravitational waveform, we assume general relativity to model the gravitational waveform, theoretical waveform template. So when we detect some gravitational wave signal, we need to really check if the prediction that GR is correct, if that actually hold. So you want to answer the question, is GR is the correct description of the gravity in the strong field regime? Strong field in the sense when the two black holes merges, the field is really strong. So you want to answer if general relativity can correctly explain this nature in the strong field regime. Also, you can ask the question, do the observed waveform, they match with the GR prediction? So we have waveform using the GR prediction and we observe some signals. So you want to answer, do the observed waveform really match with your prediction that you predicted using the GR? Is GR self-consistent across the event? Like, so this compact binary coalescence has different phases, in spiral, merger, ring down. So we want to know if GR is actually valid across all this region. Because as you go to merger, the system becomes so dynamic, so GR can be, may not be whole. So you want to test that. Also, you want to predict, you want to answer, are the black hole behaving as GR predicts? So GR predict that there will be different features in black holes. So you also want to answer those questions. Also, do the gravitational wave propagate as GR predicts? So all these questions, so when you study, you use some GR prediction, and from the observation, you want to know if whatever you predicted is actually consistent with whatever you observed. So I'm going to talk about two particular cases. So do the observed waveform match with GR prediction? So what we do here, that you have some observed signal that you are getting in the detector, and you have some waveform that you created using your GR, whatever knowledge you have. So what you do, you best fit your signal with a GR waveform, and then you find the residual between the data and the GR waveform. If the residual is kind of random and noisy, that means it's a property of the noise, property of the detector. That means the GR is correct. But if the residual has some kind of structure in it, then maybe there is some extra physics that you missed when you used GR. So by doing this residual calculation, so here this plot shows, so this dotted line is the line of zero, like it means if your residual is consistent with this line, that means there is no deviation in GR. And you can see roughly this line is almost close to this prediction, and there is no structure in this particular plot. So far the GR is correct theory of gravity in our case. Also, another test of GR that we can do is to study if GR is self-consistent across different phases of your black hole merger. So as I said, there are in spiral, merger, ring down part, and in the in spiral part, the frequency is low of the gravitational wave signal, and as you go to the merger and ring down, the frequency increases. So what you do is that, so let's give you some examples. Let's say you have two kind of dough made of some mud or something, and these doughs they are going to collapse, they are going to just merge to each other. So before merging, you know the masses of the dough and how they are moving. So from that, you can use your theory from Newtonian mechanics that how the dough will be when it merges. and you have this theory, and then when it finally merges, so you see if the final product after merging is actually consistent with what you predicted. If it is consistent, then your theory is correct. If it is not, then you need some kind of correction in your theory. So that is exactly what we are doing here. So we divide our signal into in spiral and post in spiral part. So we predict our how the waveform will look like, how the masses and spins will be after the post inspiral part from the inspiral part, and then also we know how the waveform will be in the post inspiral part. So this fractional deviation, this fractional ratio you can see in mass. So what it says, this MF in spiral is the mass of the final black hole that you predicted from your in spiral part using some theory that you know. And this MF post in spiral is the actual observed post in spiral mass. Then you find this deviation. If this deviation is zero, almost zero, then you can say the theory you predicted using the theory you assume to predict the post in spiral part is correct. Otherwise, you need some kind of correction. So you can do it final black hole mass and spin, and this is the plot showing here. So this different color, red and blue, shows for the mass and spin. So you can see almost all the lines, the deviation is consistent with zero. So no significant deviation from general relativity so far observed. So that's how you can check, you can do some consistency check using your gravitational wave observation. So there are other checks that I'm not going to talk here. So one more interesting thing to test GR is the GR predict that gravitational wave speed is the speed of light, like it propagates with the speed of light. So from this event GW17817, we observe this electromagnetic counterpart 1.2 seconds after merger. So from that we can infer that what is the speed of gravitational wave, and the speed of the gravitational wave, it is consistent with speed of light within some uncertainty limit. Another interesting thing that GR predict is that do gravitational wave lens the same way at light do? So we know the lensing of light. So GR also predict that gravitational wave can be lensed when there is some galaxy on the way of gravitational wave. Let's say this is your gravitational wave source and you are here, your detector, and if there is some galaxy in between, so this gravitational wave will be lensed and you will see two copies of the same event. This is called strong lensing. If there is some compact object, not galaxy, then your gravitational wave will be some kind of modulation, you can see, that is called microlensing. So all these effects are predicted in GR. So by observing this kind of event, you can actually tell that GR is consistent, whatever it predicted. So also you can probe the large structure universe and the matter distribution using it. So when it lends, you can actually tell the property of the galaxy in between. So you can probe into the large structure of the universe and the cosmology and so on. Okay, moving forward. So this end my science with CBC object. What kind of science we do? There are few more science we can do, but for the interest of time, I'm not talking about those. And now we'll go to the third generation detector. So if you heard about it, so currently we have like 5 detector, LIGOs and Virgo-KAGRA, and LIGO India is also ongoing. So we have some future detector, like third generation detector we call Cosmic Explorer and Einstein telescope. This will be, the sensitivity will be very high compared to the current generation detector. So this is the side of Cosmic Explorer and Einstein telescope, some artistic drawing. So, so you can see the sensitivity curve. So from yesterday, if you remember, so we are showing some noise curve. So for this Cosmic Explorer and Einstein telescope, the noise curve is very below. That means you can observe many more signal in between in this band. Also, if you notice the frequency, it's the particular detector, it can probe into very low frequency, like 5 hertz, 3 hertz. So you can see much longer waveform. Also, you can probe to very harder redshift. You can see from this plot, the current generation LIGO, it can only observe the redshift of 1 point something, but with Cosmic Explorer and Einstein telescope, you can see much more further signal. So it is another kind of diagram which shows that so this yellow dots are the neutron star, and this whites are the black holes. So currently so these are the different detector scenarios. You see O3, A+, Voyager, Cosmic Explorer 1 and ET. So these are different detectors. So currently we are in A plus scenario. So we can observe this patch of the sky, and which is corresponding to redshift of some values, so like order of 1. But if you increase the sensitivity and if you go to the C and ET, you can almost observe all the black holes and neutron stars in the universe. So this is something exciting to see in the future. So yeah, with this I'll conclude, and here is some summary of my talk. So compact binary coalescence are merger from black hole or neutron star, and from this compact binary detection we can understand the astrophysical formation and their source properties like mass, spin, and how far the sources is. Also, this detection enables to study astrophysics, gravity, cosmology, like test of Gier, and how the matter behaves in extreme condition, which is the Newton's third equation of state. Also, with very increasing sensitivity, we can detect much more CBC events. And there are many open questions that are currently people are working on, which are like this binary formation channel, and yeah, how this binary form and the modeling of those binaries. So yeah, there are much more exciting things to come. I think with this I'll end. Thank you. And I'm happy to take questions. Is there any questions? Mm-hmm.
The circular orbit waveform and the spin alignment waveform, what was the exact difference? Like,
Circular orbit and the.
so this is one waveform, quasi-circular. Could you go to the next where you showed the spin? Yeah. So aligned spin and quasi-circular, how do we distinguish which one is which? Because they look similar to that.
Like aligned spin means when you have spin aligned with your orbital angular momentum, and when I say quasi-circular, that means there is no spin. So they look exactly similar. The question is, how do you know if?
How do you distinguish whether it's no spin or aligned spin?
For that, you do something called parameter estimation. Like after detecting a signal, after getting some high signal to noise ratio of a signal, you analyze the signal in details, like what are the parameters of this particular signal, like the masses, the spins, and in that process, you know if there is some spins of the signal. You don't essentially know from the waveform itself. You do some further calculation, like the parameter estimation, to actually say that there is some spins in this detection. But from the waveform itself, yeah, you cannot say.
Okay.
One way to say, okay, for the aligned spin, if you have two signal with no spin and aligned spin, so because of the aligned spin, there can be some, like the duration can be higher, because the aligned spin systems are very stable, so they can orbit little bit longer compared to no spin system. So by looking at the duration, you can say, but not exactly how much the spin or so on. But for that, you have to do the parameter estimation study to actually. Is there any more questions? Okay, so in that case, thank you again, and